This worksheet is meant to be a challenge where you're able to practice precipitation reactions along with the concept of limiting reagent introduced earlier in the semester. So I wanted to work through it with you just so you can slow down and just kind of think. But this worksheet is supposed to cause you to think. So how do I set up a problem? What's the question asking me? Take the concepts that you've learned and put them all together and think through how we go about finding a solution. So this first question says I have lead nitrate and it's reacting with potassium sulfate. So those are your two products. The first thing you want to do is write a balanced chemical equation. So if we have lead 2, that is Pb2 plus, reacting with nitrate, NO3 minus, and here we have potassium, K plus, reacting with sulfate, SO4 2 minus. So I first need to balance my equation, which means I have lead nitrate plus potassium sulfate. Make sure you're crossing and uncrossing those charges. Yields, what's going to yield? So remember, this is where we react things together. And because when we throw everything into solution, it's all going to find oppositely charged particles. And so we need to be able to predict what might find and what might react. So this is going to produce potassium nitrate and lead sulfate. Now the 2 plus is going to cancel with the 1 plus, therefore making it so neither of them have a subscript. And now I need a balance. Notice I have 2 potassiums on the left and I only have 1 on the right. And now that I've added that 2, it is balanced. So now I need to go back in and I need to decide what is going to be a solid. So my 2 reactants are both aqueous. One has potassium, one has nitrate, so that's going to force them to be soluble. Potassium nitrate, definitely aqueous, which means lead sulfate. Absolutely, that is going to be my solid, so I'm giving it an S. And that's my question. It wants to know how much precipitate could be collected, and so that's lead sulfate. And when it says how much, you don't measure out moles on a balance, so just think that's asking you about grams. Okay, so what do we need? What do we have? Remember, if you're ever stuck, the first thing you should do is turn everything into moles. So let's do that first. I have 50 milliliters of lead 2 nitrate, 1 molar. So I've got 1.00 molar times my volume. This is in milliliters. And so since that's in milliliters, I'm going to convert that in my head to liters. If you need to do it on paper, you go right ahead. So that's going to lead to 0.05000 moles of lead 2 nitrate. Okay, now I need to get that all the way to product. So this is where my molar ratio comes in. If I convert my moles to, so I've got 1 mole, because I've got a 1 here in my balanced chemical equation, 1 mole of lead 2 nitrate. That's going to be equivalent in the reaction. It's going to have a molar ratio to 1 mole of lead 2 sulfate. And so if I do this reaction to completion, I'm going to end up with 0.0500. How many sig figs should I have? I should have 3. 0 moles. That means I have 1 too many zeros there of lead sulfate. Now let's do the other one. My other solution is 35 milliliters, and that goes with 3 molar. So I often ask the question, what goes with what? Meaning, all of this information is accompanied with the lead 2 nitrate. And all of this information goes with my potassium sulfate. Whenever you're doing molarity times volume, note that you need to make sure that the 2 numbers you're using go with the same chemical. All right, I'm going to do that down here. So I've got 3.00 molar of that solution times my volume. I'm converting that to liters, and that is going to give me 0.105 moles of potassium sulfate. And once again, I need to do my molar ratio. Why am I doing this? Well, in this case, it doesn't matter because they're all 1 to 1. But if it's ever not 1 to 1, like we're going to see below, that could make it so what you thought was the lower number is actually going to be the higher number because of the molar ratio. So in this case, this would yield 0.105 moles of potassium sulfate. And you know, not potassium sulfate, lead sulfate. And so you know from prior work that at this moment, you've got to look at your two numbers and decide which one is smaller, because you're never going to actually create 0.105 moles of lead 2 sulfate. Why not? There is not enough of the lead 2 nitrate available to actually generate that much. So that means, what is my limiting reagent? My limiting reagent is lead 2 nitrate. And so I'm going to have excess of my potassium sulfate floating around. So now I haven't entirely answered the question, but I'm really getting there. So now I take my moles of my product that was generated from my limiting reagent, and I convert that to grams, and that's my last step. So I got my moles of lead 2 sulfate multiplied by the molar mass, which is 303.261 grams of lead 2 sulfate. And that's all in 1 mole of lead 2 sulfate. And that gives me 15.2 grams of lead 2 sulfate. And so that's my final answer. That's how much would actually be created after the reaction was completed. I'm still going to have some potassium sulfate remaining, but this is the amount of precipitate that could maximally be collected. Now remember, no reaction is perfect, so you're actually going to probably generate less than that. All right, that's the first problem. Let's do the second one. What volume of 0.355 molar calcium chloride solution is required to react completely with that? So once again, I'm going to start out this time by highlighting, meaning I know all of this information goes with calcium chloride, and this information goes with sodium phosphate. And so what am I trying to find? In this case, I was looking for a precipitant. In this case, I'm not. I'm looking for calcium chloride because it says what volume of calcium chloride. So the first thing you got to do in any time a problem like this, balance the chemical equation, start converting stuff to moles, and just see where it goes. So what do I have? I don't know my volume of calcium chloride. That's what I'm solving for, so I can't multiply that one. But I do know a volume and a molarity. Anytime you have those together, then I recommend starting with that. 3.00 molar times 5.50 liters. That's going to give me 16.5 moles of sodium phosphate. But what do I do with that? Well, I haven't written my balanced chemical equation. Shame on me. So let's do that now. So I've got calcium, which is calcium 2 plus, mixing with chlorine is going to give me calcium chloride. And that's reacting with sodium. Sodium is +1. Phosphate is PO4 3 minus, which makes me have a 3 down below. Those are then going to react. Let's react the two together, meaning sodium reacts with chlorine, phosphate reacts with phosphate. So that yields sodium chloride plus calcium phosphate. I uncross those charges. So now I've got to balance, and in this case, I've got 3 sodiums on the left, but I have 2 phosphates on the right and only 1 on the left. So I need 2 of these. And so when I do that, now my phosphates are balanced, but my sodium is not. So I need to put a 6 in front of sodium chloride. And then I still have calcium chloride. If I balance out my calciums, that makes it so there's 3 on both sides. And now there are 6 chlorines overall on both sides. Check. Okay. So I've got 16.5 moles of sodium phosphate. But I'm trying to figure out calcium chloride. How do I go from one compound to another? Doesn't matter if it's reactant to reactant, product to product, reactant to product. You use the molar ratio. So whenever I need to go from one compound to the next, I just use the molar ratio. So I've got my moles of sodium phosphate, and I need to make those moles change into moles of something else. What do they need to turn into? Calcium chloride. So I've got my reaction set up, and what do I do with it? Well, you got to first figure out what numbers go here and here. So what numbers? The chemical coefficients in the balanced chemical equation. So we've got 3 on top, 2 on bottom, to give us 24.75, I'm not going to round until the end, moles of calcium chloride. All right, how does that help me? Well, we know the definition for molarity is moles per liter. What am I solving for? I'm solving for volume, so I'm trying to get liters by itself. So algebraically, this can be rearranged to big liters, or volume, is equal to moles per molarity. Okay, another way you could think about this is you could use molarity as a conversion factor, meaning that 0.355, that's 0.355 moles per every liter. And so if we took our number we just solved for, 24.75 moles of calcium chloride, and we multiply it by the molarity, this value right here, I need my 0.355 moles of calcium chloride to be on bottom, and I need 1 liter on top. Multiply these guys together, and I end up with 69.7, where I fix my sig figs, liters of calcium chloride, which is a ridiculously large number, but it is correct. So what do we do here? We balance the chemical equation. Anytime we have molarity and volumes, we multiply them together. We use the balanced chemical equation to convert from one species to another, and then we look back at our answer and say, what do we need to do with it? And that's where you're either using the limiting reagent, or in this case, it's just asking us, we're reacting it completely. So meaning, how much is going to react? 69.7 liters is. Okay, so with each of these problems, there is a pattern to it, which basically involves balancing a chemical equation, converting as much as you can to moles, but then you have to use your brain and you have to decide where do you go next. And that, I know, is a challenge sometimes, but the more you practice, the better you will be. And so practice, practice, practice. All right, let's do the next one. For this next one, we have a balanced chemical equation of, and I'm not going to go through this with you because at this point, I feel like you can figure it out by yourself. And I did not put, as I'm writing this, I realized I did not just tell you the, which one was your precipitant. So in this case, you've got aqueous because of your sodium, because of your chlorine, sodium and chlorine. So all of this is aqueous. And now, according to our solubility rules, this one is our solid. Here, same types of things. This one's my solid. This one's definitely aqueous because of nitrate. And because of your hydrogen, this one, nitrate, and your hydrogen. So this one is aqueous and aqueous. And so in this case, it says, what is the mass of the precipitate? What am I asking about? I am asking about my silver iodide. Okay, so what do we do? Remember, the first thing is convert everything to moles. And then, why not? Let's convert everything to moles of precipitant. But do also check, is it balanced? Sure is. Everything's 1 to 1 to 1. Okay, so it is all balanced. Let's start converting stuff. So I'm going to pull out my highlighter once again, and I'm going to make sure that I'm only using numbers that go with each other. So all of those values go with your hydroiodic acid. All of these numbers go with silver nitrate. The number one problem I see on exams is students will mix one value that goes with the value for another chemical. So practice this. Pull out your markers. You can pull out your markers and highlight them. I think it's helpful. So I have a molarity and I have a volume. And how do I know that that's multiplying? Well, you can either say, well, I know molarity times volume gives me moles. Or remember, molarity is the same thing as moles per liter. And you're trying to make these liters cancel out, leaving you with moles. So that is 0.125 moles of HI. All right. And once again, it is all 1 to 1, but I might as well show my work, get yourself those points. I need to convert from moles of hydroiodic acid to moles of silver iodide. Okay. And so that's going to give me 0.125 moles of silver iodide. And then let's do the next one. For the next one, I have 0.333 molar times 0.0175 liters. Once again, I did that conversion in my head. And that ends up with 0.058,275. And that is moles of silver nitrate. Do my conversion. 1 mole of silver nitrate for every 1 mole of silver iodide. And that's going to give me 0.0058275. Keeping an eye on those decimals just in case I need them later. I will round at the end, moles of silver iodide. At this point, you're like, oh yeah, it's a limiting reagent problem. I need to decide which one is smaller. So this one's bigger, which means my HI is my excess reagent. And my limiting reagent is silver nitrate, which means this is the value that goes forward. What do I need to turn it into? I need to turn those moles into grams of silver iodide. So at this point, you're like, oh yeah, I can do that. That's easy. I'm going from moles to grams, so I need to use the molar mass. So we've got in 1 mole of silver iodide, we have 234.77 grams of silver iodide to give us 1.37 grams of silver iodide. And that is the total mass at the end of a reaction, maximally, that I could produce. All right, let's do the last and final question. Let's highlight. I love doing the highlighting thing. So make sure that you're not screwing something up by combining stuff. Okay, so this time I've got that information about barium chloride. And then I've got 1.2 grams of sodium sulfate. But then what is this other random number? What do I do with this? I have a percent yield of this. And my question is different than I've asked before, because remember, we're not all about just learning a method. It's using our brain. And so that's what these questions are set up to do. I'm asking how much sodium chloride was experimentally produced in grams. Whew, what in the world? All right, so let's think through this. Let's first start out with writing our balanced chemical equation. And then we'll think about our numbers and think about what we can convert them to, hint, 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 moles, and then we'll see what we can go from there. All right, balanced chemical equation. I'm going to assume you can do this by this point. So barium chloride, that is aqueous. Did I remember aqueous? Yes, I did. So barium chloride is aqueous plus sodium sulfate. Also aqueous, thanks to that beautiful sodium there. And it yields barium sulfate, which is your solid, plus 2 sodium chlorides. All right, before we start this problem, let's think through and think about where we might be going. So meaning, this one's a little different. Instead of looking for the precipitant, which is barium sulfate, this one is saying how much sodium chloride, okay? And so it says if you start with that and you note that you have a percent yield of this, and so that yield, that percent yield, is actually of our sodium chloride. And so let's write out that percent yield formula for us. So percent yield, in our case, equals 93.27%. That equals your experimental yield. And in this problem, our experimental yield is sodium chloride. So that's grams of sodium chloride, because that's what it told us in the problem right here. Okay, over theoretical yield, which is also in grams of sodium chloride, times 100. So when we're doing our problem, this top part is the part we are trying to find out. This bottom part, how do we get that? It comes from math. Math from all of these other numbers that we have already seen in the problem. So that's what we're working toward. We're trying to get 2 grams of sodium chloride using our math, trying to figure out what is our theoretical yield. So it's a limiting reagent problem where we're trying to find a theoretical yield of sodium chloride. And then to find out how much experimentally was produced, we just put it in our percent yield formula. Okay, so that's happening at the end. Let me put a line under it so we don't get too confused. All right, so start like you do every other problem. See what you can convert to moles. So we have 0.113 moles of barium chloride per liter. Remember, that's molarity times our volume, 0.2543 liters. And then from there, let's convert that. So that's going to give us 0.00287359. Just give me a whole bunch of digits here. Barium chloride. I need to turn that into sodium chloride. So what's my balanced chemical equation? In this case, 1 mole of barium chloride to every 2 moles, because of our coefficient in front of sodium chloride, of sodium chloride. And that is going to give us 0.00574 moles of sodium chloride. But that's not a theoretical yield yet, because we need to make sure that that's not our excess reagent. So the next one is where we got to start is, what do we have the information about sodium sulfate? So we have 1.20 grams of sodium sulfate. How do I get to moles of sodium chloride? I know you know this. So you got grams. We go back to molar mass. 142.041 grams of sodium sulfate per every 1 mole of sodium sulfate. Then I need to convert from sodium sulfate to my product, which is sodium chloride. And so I use my coefficients and my balanced chemical equation, and that is going to give me 0.01689 moles of sodium chloride. Now, which number do I use? Remember, this is the part where you ask yourself, which one is smaller? This one's smaller, so that one goes forward. This one, therefore, is in excess. That makes this my limiting reagent and this my excess reagent. So we need to go forward using this 0.00574 moles of sodium chloride, and I'm trying to get it to grams. So we use our molar mass, 58.443 grams of sodium chloride per every 1 mole of sodium chloride. And that's going to give me 0.335 grams of sodium chloride. Now, what is that number? That is my theoretical yield. That is not how much was actually produced because we were given our percent yield. So now we come back to our percent yield formula that we used at the beginning. 93.27% equals my experimental yield over my theoretical yield times 100%. And that equals an experimental yield of 0.312 grams of sodium chloride, which makes sense because my percent yield is just a little bit less than 100%. So I get just a little bit less sodium chloride than I should have produced. And with that, you can see how each of these is different, but they have the same kind of idea. You write a balanced chemical equation, you use your brain to convert it to moles, and then you use your brain a little bit more to figure out what to do next. I hope this video was helpful to you.